This video will teach you how to analyze angled launch projectile motion problems. We'll start with some basic information that you'll need to know, and then we'll move on to analyzing a problem together, and finally a problem on your own. First of all, it's important to know that one of our first steps, after we draw a picture of the situation, is to split the initial velocity into its x and y components. Now you'll see here I call those Vix and Viy. It's important to note that Vix is the same thing as V sub x, as we've been using in the previous problems. Once we do that, we'll analyze the problem like we typically would. However, there's a couple of hints that'll help you analyze these problems. For starters, sometimes it might be useful to set the final position to be at the maximum height. At this location, the final velocity in the y direction is equal to 0. Does that mean that this object is not moving? If you answered no, you're correct. That's because the object still has an x velocity. It's just not moving in the y direction. So its total velocity at its maximum height is just pointed left or right. The other hints refer to a situation where delta y is 0. In other words, an object begins and ends at the same height. Some real-life examples of this include a football being kicked to a goal, a golf ball being hit across a level green, or someone simply throwing something up in the air and catching it at the same height. When that's the case, there's a couple of important facts that we know. For starters, the time that it takes our projectile to get to its maximum height is half of the total time of flight. Also, the x displacement to the position where the maximum height occurs is half of the total x displacement. This should make sense if you think about the path of our projectile. We talked about the path being a parabola. So it would take half of the time to get up there and half of the time to get back down, in the same way that it would take half of the x distance to get to that maximum point. We'll use these facts, as well as things we already know about projectile motion, to analyze our first example problem. In this example, a stuntman is jumping from the top of one building to the top of another building that is 4 meters away. The stuntman gets a running start, leaps at a velocity of 5 meters per second and an angle of 15 degrees with respect to the flat roof, and we want to know if he's going to make it safely onto the second roof, which is 2.5 meters lower than the building he jumps from. Just as with horizontally launched projectiles, we'll start by drawing a diagram. I have one building, and then a second building that's a bit lower. I'm going to add in the information that I know from the problem. For example, I know that the distance between the two buildings is equal to 4 meters. I know that the height difference, we'll mark that like so, is equal to 2.5 meters. Lastly, I know that our man is located at the top of this roof and is jumping like so. There's the path that tells me he has an initial velocity of 5 meters per second and an angle of 15 degrees. Okay, so based on this information, we're now going to write down what we are given. As I mentioned to you before, the first thing that we do is split up that initial velocity into x and y components. This is something that we've already learned how to do, and so I will just go ahead and give you those components. In this case, the x velocity is 4.83 meters per second, and the initial y velocity is equal to 1.29 meters per second. Remember that I suggest drawing a diagram that includes that initial velocity vector, 5.0 meters per second, and the x and y components, like so. If I draw that diagram, that angle that I am given, 15 degrees, is located right there. Okay, so let's find out some of the other things we're given. That 4 meters, that's an x displacement. Delta x is 4 meters. And we know also that ax is equal to 0. In the y direction, we also know several things. For example, we know that our person is going to drop 2.5 meters. That means delta y is equal to negative 2.5 meters. We know that our y acceleration is negative 9.8 meters per second squared. Based on this information, we can calculate what we need to know. The problem is asking, will he make it to that roof? 2.5 meters lower. Well, to be able to calculate that, there's a bunch of things that we could do. The method that I'm going to show you is to figure out how much time it takes him to drop 2.5 meters, and then we'll see if he travels 4 or more meters during that time. In other words, this given, the delta x equals 4 meters, is not something that I'm going to use in my calculations. So I'm going to start looking at the y direction. In the y direction, I'm given several pieces of information, and it's enough information to be able to calculate the amount of time that it takes. Based on what I know and what I'm looking for, the equation you might pick up first says delta y equals VIYT plus 1/2 AYT squared. However, solving for time in this equation is going to require a quadratic formula, which isn't everyone's favorite. So I'm going to show you another method. Instead of using this equation and having to use the quadratic formula, I'm going to start by calculating the final velocity of our man. I can do that using the equation v final y squared equals v initial y squared plus 2 ay delta y. I don't have to do much rearranging to solve for v final y. I simply need to take the square root. Now, I'm going to add in something you've learned in math class in the past, and that's the fact that really when you're taking the square root of both sides, the value is equal to the positive or negative square root of VIY squared plus 2AY delta y. We'll talk about what to do with that plus or minus once we get our number. So that means that VFY is the square root of 1.29 meters per second squared plus 2 times negative 9.8 meters per second squared times negative 2.5 meters. Once you plug all of that into your calculator, you'll end up with a value of 7.1 meters per second. Now, I told you we'd deal with that plus or minus in a minute. If I think about my diagram, I notice that my person is going downward when he gets to the second building. He's kind of going at an angle, but in the y direction it would be down, not up. And that means that that plus or minus really becomes a minus, showing the direction of that final velocity. Now that I have final velocity, I can calculate time using a couple of different equations, but I suggest to use the equation VFY equals VIY plus AYT. This equation is probably the easiest one to use because it's easiest to solve for time here. I'll start by subtracting VIY from both sides. And then I'll divide both sides by AY. So that time is equal to VFY minus VIY divided by AY. Or in other words, negative 7.1 meters per second minus 1.29 meters per second divided by negative 9.8 meters per second squared. This yields a time of 0.86 seconds. Now that I know that time, I'm going to use it to calculate the x displacement that he travels in those 0.86 seconds. I use my one and only x direction equation. Vx is delta x over delta t. Solving for delta x gives me Vx times delta t, which is 4.83 meters per second times 0.86 seconds. That gives a value of 4.1 meters. Now let's compare that to the delta x between the two buildings. It's 4 meters between the two buildings. That means that our stuntman just barely makes it, which is what we usually want in an action movie. We don't want him to be super safe, we want him to just barely make it. So the answer is yes, he does make it to the other roof. Let's look at another angled launch problem. In this problem, we have a golfer hitting a golf ball at a speed of 40 meters per second at an angle of 25 degrees to the ground. We know that the golf ball covers a horizontal distance of 301.5 meters. We want to know the ball's maximum height. Okay, so let's start out drawing a diagram of what we have here. We have nice level ground. And I don't care so much about the golfer, I really just care about the golf ball. Its path is a nice parabola. Starts out with a speed of 40 meters per second and an angle of 25 degrees. We also know the horizontal distance to be 301.5 meters. Now we're going to list our givens. Right now I'd like you to pause the video, list the givens for yourself, and then unpause it so you can figure out if you got them all. The very first thing you should have done is split your initial velocity into its x and y components. If you did this correctly, you would have gotten 36.3 meters per second for the x component and 16.9 meters per second for the y component. You should, of course, have both accelerations listed. And then one of the numbers given to you in the problem is 301.5 meters. And something else that you can tell from the diagram is that delta y is 0. In other words, it begins and ends at the same height. I wanted to put these up here so that I had a good point to tell you about the fact that the last two pieces of information I've written here are not useful to this problem. The reason they're not useful is the problem asks, what is the ball's maximum height? In other words, the problem is looking for this delta y value. That means that I'm actually going to set my final location to be at this maximum height. In other words, I don't care about the rest of the path of this ball. I'm just going to look at that first half. Because that's the case, I know that V final y equals 0. That was one of our facts under the hints section. Using this information, I'm now going to try to solve for delta y. It's your turn now. Take all this information that we know, look at your equations, and try and solve for delta y, or the maximum height of the golf ball.